Hello everyone, we are back to the wonderful world of calculus, and we are now going to focus on the differentiability of a function at a given point. We have seen in the previous presentation that the rate of change, or the derivative, of a function y equals f of x at coordinate point a, f of a, is obtained from either f prime of a, which is the limit as b goes towards a, of f of b minus f of a over b minus a. If it were not for the limit, this ratio would be the slope of a secant line through two distinct points. So if you remember, the limit process brings the points closer and closer together, making what used to be a secant line become eventually a tangent line, and the derivative measures the slope of that tangent line. In terms of notation, using x rather than b would make no difference. And there is an alternative definition where, rather than having x or b, we denote the second point as a plus h. So it's a point that is h units before or after, because it could be a negative number, the point a itself. And at the bottom, h is the separation in the x-coordinate. So in all three cases, we're doing delta y over delta x. It's just the formulation that is slightly different. Of course, this derivative is only valid when the limit actually exists. That's very important. The derivative is the result of a limit calculation. So if f prime at a, which is denoted by the limit as b goes towards a of f of b minus f of a over b minus a, so if this limit exists and is finite, we say that the function is differentiable at x equals a. However, if this same limit does not exist or results in an infinite value, then the function is non-differentiable at x equals a. Example number 1. Is function f of x equal root of x differentiable at x equals 4? Let's note first of all that f is continuous in the neighborhood of x equals 4 since it is a root function and its domain allows for all values of x that are greater or equal to 0. So we're not at the border of the domain, we're well within the domain where the function is clearly going to be continuous. So now we're set. I've set up the definition of the derivative of a function at a. Now in this particular scenario, we said we wanted to verify if the function is differentiable at 4. So the value we would use for a would be 4. B remains a variable whose value depends on the way in which we approach 4. So there's a b value which is varying. So f of b will be root of b because f of x is root of x. In the same manner, f at 4 is root of 4. We can simplify root of 4 down to 2. If we try direct substitution, this would result in a 0 over 0 form. So we're ready to move on, and to solve this 0 over 0 form, the use of rationalization probably comes to mind. So we're going to multiply by the conjugate of root b minus 2, which happens to be root b plus 2, obviously above and below. If we expand the numerator, root of b minus 2 times root of b plus 2 results in b minus 4. And we have now highlighted a common factor that can be eliminated, which leads us to be now able to do direct substitution. As b goes towards 4, 1 over root of b plus 2 will head towards a quarter. So the result we are getting exists and is finite. So the function y equals root of x is differentiable at x equals 4, and we can even go beyond that and say that f prime at 4 is a quarter. This means that the slope of the tangent line to the curve at 0.4 1/2 is equal to a quarter. Remember that the coordinate points only depend on the xy relationship, whereas the slope is what f prime at 4 is measuring. So graphically, here is what we've obtained. We have our root function at coordinate point x equals 4. The y component is 2. And according to our calculations, the slope of the tangent line, which appears in orange, is 1/4. That seems to make sense graphically anyway. Here's a bit of a special scenario where we have a function that is defined piecewise. So two different rules depending on the region where we're examining it. So is the function, first of all, continuous at x equals 0? And secondly, is the function differentiable at x equals 0? These are very, very different questions. Starting with continuity, first of all. So recall the definition that we have for continuity. We need to verify that the function's value at a agrees with the function's limit as x approaches a. Because we have a piecewise function, this cannot be done in one single step. We're going to have to look at both left and right hand limits. In particular, in this case, the change in rule occurs at 0. So I've adapted the definition of continuity to the scenario where the switch takes place at 0. So first and foremost, the function's value at 0 was given by the second portion of the piecewise definition, which was the parabolic or quadratic term. 0 squared minus 3 times 0 is 0. So the function does exist at 0 and its value is 0. Essentially, this function goes towards the origin, or is at the origin when x is 0. As for the left-hand limit, as x approaches 0 from the left, the function's rule to use is sine of x. Sine of x is continuous. By direct substitution, we obtain a 0 result. The right-hand approach can also be done by direct substitution, as we are dealing with a polynomial, and another 0 result is obtained. So in this case, the function's value, as well as both one-sided limits, all agree to take on the value 0, and therefore f of x is definitely continuous at 0. When having to answer the question on the function's differentiability, we have to remind ourselves of what being differentiable means at some point a. So here is our limit definition of a function's derivative at a. So limit as b approaches a, f of b minus f of a over b minus a. In our specific example, we are heading towards 0, where the connection point takes place. So f prime at 0 is defined as long as this limit exists. Now, remember, if b is going towards 0, it could go towards 0 from the left or from the right, and we are using different functions, f at b, when doing these evaluations. We're going to split this into two different situations. The first situation involves looking at the limit as x approaches, or in this case as b approaches 0 from the left. I've used a new notation to indicate the fact we're evaluating the tangent line slope from the left side of the connection point. I've written f prime at 0 minus. This is not standard notation, but I think it conveys well the idea that we are evaluating the derivative for the left-hand function approaching 0. Now, to the left of 0, f at b is evaluated using the sine function. So sine at b minus 0, by the way, we're subtracting 0 not because sine of 0 is 0, but because f at 0 is 0. We evaluated it specifically beforehand. At the denominator, b minus 0. Now we can simplify to sine of b over b as b approaches 0, and that is a recognizable special limit whose value is 1. So the function's derivative, or if you prefer the slope of the function as it approaches 0 from the left-hand side, is 1. The right-hand approach, symbolized by f prime 0 plus, is obtained by evaluating f at b minus f at 0 over b minus 0, and then performing a limit to push b towards 0. Now to the right of 0, we're using the parabolic function, or the quadratic. So I've replaced f of b by b squared minus 3b. F at 0 is still 0. Our denominator is b minus 0 by definition. If we cancel the zeros and factor the numerator, we can then simplify our rational expression and reevaluate the limit to obtain minus 3. So the function to the right of 0 leaves with a slope of minus 3. And already we can see there is a contradiction between the slopes we are observing. If you remember, by definition, the limit has to exist, which means left and right hand limits should agree. So since the left hand limit that we obtained gives us or provides us a limit result of 1, and the right hand derivative to 0 provides us a limit of minus 3, then we cannot remove the b heading towards 0 from left or right and combine them as a b going towards 0 globally. We have diverging limit left and right hand limits. So because this limit doesn't exist, then f prime cannot exist at 0, and we would just conclude that f is not differentiable. At 0 specifically, obviously. Graphically, what we have evaluated is that the slope of the function coming in from the left does so with a slope of 1, or the function approaching from the left does so with a slope of 1, but it leaves from 0 with a slope of minus 3. So the transition here is not done smoothly, and that's one good way of thinking of differentiability. So does the connection occur smoothly? And here clearly it does not. So we get a pointy edge. Our last example, so is the function cube root of x continuous at x equals 0, and is it differentiable at x equals 0? Again, two different questions. One is about the continuity of the function, the other one is about its differentiability. So first, maybe just out of memory, remember that cube root of x is continuous at x equals 0. In fact, the cube root function belongs to the list of functions that are continuous on their domain, which happens to be all real numbers. So x equals 0 does not create any problematic situations here. The function is continuous all the time, notably at 0. Differentiability requires we go back to the definition. In this particular case, since there is no change in definition, this is not a piecewise function, we need not apply two different limits. So I've done one single limit, applying the rule f of b minus f of 0 over b minus 0. The root of the cube root of b is how f at b is defined, canceling off the zeros and using our laws of exponents. We notice that at the top, cube root of b is b to the 1/3, and at the bottom we have b to the power 1. So our rules of exponents allows us to reduce this to 1 over b to the 2/3. By direct substitution, what we observe is a 1 over 0 plus form. 0 plus because at the bottom we're doing b to the power 2/3, so we're actually squaring b, followed up by a cube root, definitely a positive outcome, and therefore the slope is infinite. The slope would be infinite here from both approaches, from the left and the right. But nonetheless, differentiability requires we have a finite number. Okay, so in this case, because the limit is infinite, the derivative is undefined, or if you prefer, f is not differentiable. Graphically, what we actually get to interpret here is that f has a vertical tangent line. So not a vertical asymptote, a vertical tangent line at x equals 0. Here is our cube root function, and what we've examined is that the function has this infinite trend when it passes through x equals 0. So the tangent line is perfectly vertical, which means it has an infinite slope. So vertical tangent line at the